Swayam Prabha, free DTH channel for education.
Greetings. We'll continue our discussion on teleportation. We have already considered two cases of teleportation in which we found that Alice succeeded in teleporting a quantum of information, which is a superposition state of 0 and 1. She doesn't know what exactly the superposition is, because the coefficients in the superposition A0 and A1 are unknown to her. They, of course, cannot be known, because if she makes a measurement, the system will collapse into an eigenstate of the measurement. And this is the quantum of information that she would send to Bob, who is at a remote location, using entanglement. And in the previous two cases, we found that this is achievable, although some ancillary support, extra support is required from some other infrastructure. She had to use a classical channel to communicate some information. And the limits of information transfer, which are imposed by the speed of light, are not compromised at any stage. So we used the Bell states, and there are 4 Bell states which are possible. And the extra infrastructure which Alice and Bob used to achieve teleportation was another 2 quantum bits, which we call as qubit number 2 and qubit number 3, and they were in a Bell state. And that is what we used to eventually teleport the information in qubit number 1, because qubit number 2, which is a part of the entangled Bell state, is left behind with Alice, and Bob moves away to a remote location with qubit number 3. So that is what we had. And the 2 cases we considered involved Alice entangling qubit 1 and 2 in a Bell state in which her qubit 1 and qubit 2 would be anti-parallel to each other. So if one is 0, the other is 1. And if the first one is 1, the second is 0. But the superposition is with a minus sign. So this is Bell state number 4 in our catalog, although it can always be written differently. In the second case, she entangled qubit number 1 and qubit number 2 in Bell state number 3 in our catalog, in which again the qubit 1 and qubit 2 had anti-parallel alignment. So if one was 0, the other was 1. First one was 1, the other was 0. But this time the superposition was with a plus state. This is what we call as Bell state number 3. However, in both of these, the Bell state in which the initial Bell state of qubit number 2 and qubit number 3 was the same. And mind you, there are 4 possible Bell states. So in as much as Alice could entangle 2 and 1 in any one of the 4 Bell states, and we already considered 2 of those cases, the other 2 can also be handled using the same kind of logic. The initial Bell state between Alice and Bob, which is the Bell state of qubit number 2 and qubit number 3, could also be one of the 4. But what we considered in both the cases that we have dealt with so far The initial entanglement of qubit number 2 and 3 was common. And now we consider a third case in which the initial Bell state of qubit number 2 and qubit number 3, so they are paired in an entangled Bell state. The dynamics is therefore correlated, but this Bell state is different from that of the previous two. So these discussions in which we deal with different situations give us the confidence that the methodology is independent of any particular choice of the Bell state that one may make for the initial Bell state of particle 2 and particle 3. It is also, of course, independent of which Bell state Alice chooses to entangle particle 2 with particle 1. But while doing so, while dealing with these different cases, we not only convince ourselves about the generality of our overall conclusions, we also acquaint ourselves with different parts of the methodology. For example, in the second case, we also dealt with how magnetic resonance is used to allow the state vector to evolve for a certain length of time, and so that the phase of the qubit could be changed through pi. Phase of the second qubit could be changed through pi. So we learned something about that technique as well. And now in this third case, we will again not only have a more general platform for our conclusions, but we will also use some other techniques which are used in the methodology in quantum information science. What we will do is we will have Alice use the control NOT gate to entangle qubit 1 and qubit 2. So we also get a glimpse of some other part of the methodology in quantum information science. So now we have a different initial state of qubit 2 and qubit 3. Qubit 3 has now been moved away from Alice to a remote location by Bob. He is far away from Alice, could be in another country or another galaxy or wherever. And Alice is left with qubit number 1, which is to be teleported to Bob at a remote location. But she also has with her qubit number 2, which is entangled with qubit 3. So Alice now has 2 qubits. She has the qubit 1 and qubit 2. Qubit 2 is in a state of entanglement with qubit 3, but she has both the original qubit, which is this, and then she has a qubit 2, which is entangled with Bob. And the overall state vector of the 3-qubit system is the product of this vector and the Bell state of qubit 2 and qubit 3. This Bell state, of course, cannot be factored, but the 3-qubit system is generated through this tensor product. It's a direct product of this vector and the Bell state. So let us spell out this 3-qubit vector. It is a vector of 3 qubits, 1, 2, and 3. 1 and 2 are with Alice, third is with Bob. And this is a product of these 2 terms and these 2 terms. So you get a total of 4 terms over here. And we write out these 4 terms as a superposition of 3-qubit states with appropriate coefficients, A0 coming from here and here, and A1 coming from here and here. So this is the 3-qubit vector. And Alice would now use the control NOT gate because she has qubit 1 and qubit 2 with her, she is in physical possession of these two qubits, and she would entangle qubit 2 with qubit 1. And toward this goal, she would use qubit 1 as the control qubit and the state of qubit 2 as the target qubit. Now, an arbitrary 2-qubit state in general is written as a superposition of these 4 possible orientations of the individual vectors. So 0, 0, 0, 1, 1, 0, and 1, 1, with 4 different coefficients such that the sum of the modulus squares of these coefficients adds up to 1. This is for a normalized state. And you have 0, 0, 0, 1, 1, 0, 1, 1 over here. And if you look at the qubits which are in possession with Alice, which is qubit number 1 and 2, which are the first 2 in each of these 4 vectors. And in the first 2, you have these possibilities 0, 0, 0, 1, 1, 0, and 1, 1. So this is the 2-qubit state, which is with Alice. So she's going to use the control NOT gate, in which she would use the first qubit as the control qubit and the second qubit as the target qubit. And remember that the control NOT gate inverts the target qubit if and only if the control qubit is in the spin down state. Of course, your qubit need not be a spin system, it can be something else, but the spin half system is a great example to work with. So that will be our prototype of qubits. So her control qubit must be in the state 1, which is a state down, and only when this is true, the target qubit can be inverted or will be inverted. So this is the result of the control NOT gate on the 2-qubit state. So this is a 2-qubit quantum gate. It will give you a new vector, which I will denote by a prime here, a single prime here. And in this single prime vector on the right hand side, the target qubit would be inverted if and only if the control qubit is 1, spin down. So this is the universal gate. So this is the matrix representation of the control NOT gate. It will operate on this vector and give you a new vector in which, notice that this 0 becomes 1 and this 1 becomes 0 because the target is, because the control is 1 and 1 in this case, whereas in the first 2 rows, the control qubit is in the state 0. So the target remains unaffected in 0 and 1, which is what you find on the right hand side. So this is the result of the control NOT gate, and the target is unchanged whenever the control qubit is in the state 0, but it gets inverted. It gets knotted, as you might want to call it. All right, this is the poly NOT gate. It becomes inverted whenever the control qubit is in the state 1. So that is what it is in the lowest 2 rows, and this is when the target is inverted. So this is the circuit, the representation of the control NOT gate. So just to remind you, so it has got this symbol which is like the exclusive OR gate in classical gates. We have discussed this in some other lecture earlier in this course, and I would just remind you of that. This is the matrix representation of the control NOT gate. And we have this 3-qubit vector, which we just discussed. One will be used as the control node. So this is the control qubit, and this qubit number 2 is the target qubit. Okay, so in this case, the control is 1 and the target is 0. In here, the control is 1 and the target is 1. So control qubit being 1, the target will be inverted for these two terms. Whereas in the first two terms, the control qubit is 0 and here also the control qubit is 0. So the target will remain whatever it was. This is not going to be inverted. It is in these two terms that the target will get inverted. So you apply the control NOT gate with qubit 1 as the control qubit and control and the qubit number 2 as the target qubit, and it entangles the two qubits. You know that the control NOT gate works as an entangler. It also works as a detangler, depending on how you really work with it. So the result of the control NOT is that the target is inverted for these two vectors. So for these two vectors, the target is inverted. It was 0 over here. It becomes 1. In this case, this target qubit is in a state 1 and it becomes 0. This is inverted. So the target is inverted, and this is what you get as a result of entangling qubit 1 and qubit 2 using the control NOT gate. So this is the result that you get on the operation by Alice on qubit number 1 and qubit number 2, which are in her possession. And now just have a look at what Alice has. Alice has qubit number 1 in this state. It's a superposition of this and this, and with coefficient A0, but she also has a superposition of 1 with coefficients A1 over here. So this is what, so this vector is common to the first two terms, A0, 0, this is common. So you factor it out and write the remaining terms over here. And this is what happens to qubit number 2 and 3 as a result of this. Okay, so this is qubit number 2 and 3. This is qubit number 1. And qubit number 1, which is with Alice, you will notice that it is the same state which it had to begin with. And naturally so, because it has only been used as a control qubit. Nothing is going to happen to it. Whatever happens is only to the target qubit, and only in the case when the control qubit is in the spin down state. So the control qubit leaves the qubit 1 alone. It remains, it continues to be in the same original state of superposition that Alice had to begin with. And what Bob has with him is qubit number 3, but qubit number 3 is in a state which is superposed with qubit number 2, and this is the superposition in which qubit number 3 finds itself. Now qubit number 1 is with Alice, so Alice can perform some operation on that, and she can do a single qubit Hadamard operation on qubit number 1 after it is entangled with qubit 2. And this Hadamard would impact the qubit 1. But because qubit 1 is entangled with qubit 2, it will impact qubit 2 also. And that is how information is communicated. So that is a strategy which is now being applied. Alice applies the Hadamard operation on qubit number 1. As a result of which, qubit 1 will not remain in this state anymore. And let us see what happens to it. So this is the primed vector which you got after the operation of the control knot, which entangled qubit 1 and qubit 2. This is what we got from the previous slide. And if the Hadamard operates on qubit 1 for an arbitrary qubit with coefficients alpha 0 and alpha 1, the Hadamard would give you new vectors in which alpha 0 and alpha 1 will be mixed. Now, mind you, if the Hadamard operates one more time, it can also unmix it. So the Hadamard will give you a superposition, all right? And it operates on these states on qubit number 1, which is with Alice. And what the Hadamard does is to create a superposition of alpha 0 and alpha 1, and it creates two different superpositions, giving you two linearly independent vectors. So you can have the Hadamard basis as an alternative basis for the qubit, and you can represent a vector as a superposition in the Hadamard states also. So you have alpha 0 plus alpha 1 as one possibility, and alpha 0 minus alpha 1 as the other possibility. There is, of course, a 1 over root 2, which takes care of the normalization. And with this, on operating on the qubit 1 by the Hadamard, Alice changes the qubit 1, and with it, what changes is the state of the 3-qubit system. So the 3-qubit system now changes from single primed vector to a double primed vector. And in the double primed vector, you have this Hadamard superposition of 0 and 1 over here. And also in this term, so you get 0 and 1 superposition. The first is with the plus sign, and the second is with the minus sign. And there is this 1 over root 2 factor, which takes care of the normalization. But now this root 2 can be taken outside the bracket and combined with this, so that you will have the overall normalization factor as 1 over 2. But there are 4 terms over here, so that's fine, that's good. So this is the double primed vector in which the 3-qubit system finds itself. So this is after the Hadamard operated on qubit number 1. So now this double primed qubit vector is this. This part is with Alice. This is qubit number 1 with Alice. And this is now the state of qubit 2 and qubit 3, of which qubit 3 is with Bob. Qubit 3 is with Bob, who has moved away. So let us see what this turns out to be. So we have got these terms. So I have 1 over root 2 over here gives me a factor of 1/2. So it is the same vector, the double prime vector, which I have rewritten here, nothing new in it. But I'm now going to multiply these terms out. So there are 2 terms over here and another 2 over here. So I will have a total of 4 plus 4, 8 terms. And these are the 8 terms which we get. And they are with appropriate coefficients A0 and A1. But remember, there is a minus sign here. So you have to very carefully watch it. And it is this minus sign which is showing up over here and here. So you have these 8 terms. And Alice is in control of qubit number 1 and 2. They are in her possession, and she can find out what is it that she has. So let us see what is it that she has. So we will factor this in a different way. We will write this as what is with Alice and what is with Bob. Here, this is of course with Alice, this is with Alice, and this is with Bob, but these two are with Alice. So let us rewrite these states, because she can carry out measurements on qubits 1 and qubit 2 to determine their states. So whatever is with Alice, these two, we have rewritten the same vector. There's nothing new in it, but it's only the manner in which we have written the 3-qubit vector as a product of 2 qubits and the third qubit that is written differently, because we have combined whatever is with Alice and whatever is with Bob. From the first term, we do the same thing in the second term. This is with Alice, this is with Bob. Over here, this is with Alice, this is with Bob, this is with Alice, this is with Bob. And essentially, Bob has got qubit number 3. So what is on the right of this line is with Bob over here, and what is on the left of this line is with Alice. Because Alice is in possession of qubit number 1 and qubit number 2, and she can find out what is it that she has by carrying out measurements. And her measurement will reveal to her if she has 0, 0 or 1, 0 in the 2 qubits, are both up, or one is up and the other is down, or is the first down, is the first up and the second is down, or both are down. And she can do measurements because she is in possession of qubit number 1 and 2. So she carries out this measurement and she will get an answer which is going to be one of these. It's either 0, 0 or 1, 0 or 0, 1 or 1, 1. And if Alice finds that she has a 0, 0, then Bob must have this superposition. Both the states are part of a quantum superposition, and Bob has qubit number 3 with him, and Bob has this superposition, which is just the quantum superposition that Alice wanted to teleport, and Bob already has it. But how does Bob know that Alice has got 0, 0? Because she may have got 1, 0. And that is a missing piece of information which will have to be communicated by Alice to Bob using a classical channel. Okay, she can shine laser light or whatever. So if Alice gets 1, 0, Bob doesn't have the original quantum superposition, but he can manipulate that. Okay, so Bob has this superposition if Alice gets 1, 0. If Alice has 0, 1, then Bob has another different superposition, which is similar to this, except that it must undergo through a poly NOT gate to give you the original. And depending on what Alice finds, Bob has got a different superposition and a different quantum state. So if Alice measures 0, 0, Bob already has the original quantum information and teleportation is achieved, except that Bob would know it only if Alice would tell him that she got a 0, 0. If Alice measures 1, 0 and Bob has got the corresponding factor for the qubit number 3, and this is no longer the original quantum information and teleportation is not achieved as yet. However, if Alice tells him that she has got 1, 0, then Bob can apply the poly Z gate to get the original one. And why would Bob do that? Because you can see that this vector is the same as this except for this sign over here, which means that the phase of the south pole must be changed, which means that you have to rotate the the block sphere about the z-axis through pi. And this is what the phase gate would do, which is the poly Z gate. If Alice measured 0, 1, and she informs Bob that she got 0, 1, then Bob would apply the poly NOT gate, because this state is the exact opposite of what Alice originally had. Instead of 0, he has got 1, and instead of 1, he has got 0. So now poly NOT gate will be applied by Bob, and when he applies that, he will get the information that Alice had in the original gate, and the teleportation is completed. Finally, if Alice measured both to be spin down, then Bob has to apply the poly NOT gate to invert them and then change the phase. So he applies the ZX gate to get the original state which Alice wanted to teleport. So teleportation is achieved, however, only after having some ancillary support, which is the state of entanglement between qubit number 2 and qubit number 3, which is a different one from what we considered in the first two cases. But then we also recognized that how a control NOT gate can be used in this operation. And in the last part, of course, Alice had to inform Bob using a classical channel as to what is it that she measured with the two qubits which are in her position, qubit number 1 and qubit number 2. So Alice informs Bob using a classical communication channel, and this, of course, can be done only at a speed less than the speed of light. Even if she uses a laser pulse to send a signal to an encoded signal which Bob can interpret so that he can figure out what is it that Alice has found. And this cannot happen at a speed which is faster than the speed of light, although entanglement is always there. It's not that it travels faster than the speed of light. It doesn't mean that it travels instantly. It doesn't need to travel. It's always there. It's just there between two entangled qubits. And that entanglement is the law of nature. This is where we find that Niels Bohr's insight in quantum mechanics was very complete, although it was sort of ratified almost 30 years later after Bohr's arguments in John Bell's theorem. But now you know that, okay, Alice has done various things with her qubit. In the first step, she used it as a control NOT gate. That didn't change the original qubit. But when she applied the Hadamard, she changed the original qubit. So it has undergone a transformation. It is no longer the same superposition that she had to begin with, and the original state is destroyed. This is therefore not cloning. In cloning, the original is not destroyed. You get a copy of the original, but the original survives. This is not cloning. This is teleportation. So quantum information has been passed using entanglement, but you have also used a classical channel. You have not compromised the limits of the special theory of relativity, but you have exploited entanglement. And I would like to reiterate the fact that it is not that information travels instantly. Information is always there between entangled qubits. So thank you all very much, and goodbye for now.